In today's lecture, we will explore a powerful yet an often unappreciated mathematical tool, Bessel function, mainly in the context of frequency modulation from angle modulation. We will understand what these Bessel functions represent, why they matter in the frequency modulation, and how they control the amplitude of the carrier and sidebands of the frequency modulation. We will also see how the carrier can completely vanish at specific value of modulation index beta. So let's get started. Let's recall the basic structure of the frequency modulated signal. The general expression for the angle modulated signal is st is equal to ac cos 2 pi fct plus phi t. In the frequency modulation, this phase term becomes phi t is equal to beta sin 2 pi fmt. So the frequency modulated signal can be written as st is equal to ac cos 2 pi fct plus beta sin 2 pi fmt. Now this expression cannot be simplified easily using the elementary trigonometric identities, but thanks to Fourier series expansion, we can write this frequency modulated signal as a sum of infinite cosine terms, each with different frequency shifts. This is where the Bessel function come in. Using the Fourier series expansion, this signal is expressed as an infinite sum of sinusoidal components, or st is equal to ac summation from n equal to minus infinity to infinity j and beta cos 2 pi fc plus n fm into t. Here, j and beta are the Bessel functions of the first kind of the order n, and they determine the amplitude of the each frequency component at fc plus nfm. These frequencies are the carrier for n equal to 0 and the sidebands for n equal to plus minus 1, plus minus 2, and so on. And also the modulation index beta is defined as beta is equal to fm by del f, where del f is the peak frequency deviation and fm is the modulating signal frequency. Expanding the right hand side of the equation term by term and noting the fact that st is equal to ac j0 beta cos omega ct plus ac common j1 beta cos omega c plus omega m into t minus cos omega c minus omega m into t plus j2 beta cos omega c plus 2 omega m into t plus cos omega c minus 2 omega m into t plus j3 beta cos omega c plus 3 omega m into t minus cos omega c minus 3 omega m into t plus an infinite number of such terms. Here, AC J0 beta is the amplitude of the carrier at the frequency Fc, AC J1 beta is the amplitude of the first sideband frequency at the frequency Fc plus Fm, and AC J2 beta is the amplitude of the second side frequency at the frequency Fc minus Fm, and so on. So the frequency modulated signal is consists of an infinite number of frequency components located at Fc plus nFm, where J and beta determines the amplitude of each component, and amplitude of components are given by AC J0 beta, AC J1 beta, AC J2 beta up to AC J and beta. Later, when we plot the spectrum of the frequency modulated signal, you will see the carrier and the sidebands spaced at intervals of FM with the heights determined by these Bessel function. Finally, we can write the nth order Bessel function of the first kind, and nth order Bessel function of the first kind is defined by the integral j and beta is equal to integration from minus pi to pi e to the power j beta sin 2 pi fmt minus 2 pi n fmt into dt. In the last lecture, we defined x equal to 2 pi fmt and dx equal to 2 pi fm dt. So the expression becomes j and beta is equal to 1 by 2 pi integration from minus pi to pi e to the power j beta sin x minus nx into dx. Graphically, this function looks like this. As you can see, the functions exhibit an oscillatory behavior similar to sinusoidal waves but with varying amplitude. Here, j and beta oscillates like a sine wave with a decreasing amplitude as the beta increases. Higher n values cause more zero crossing and start from 0 at beta equal to 0. J and beta starts at 1 while j not beta starts at 1 while j and beta is equal to 0 at beta equal to 0 for n greater than or equal to 1. J not beta equal to 0 at beta is equal to 2.405, 5.520 and 8.654. These are called carrier nulls. At those beta values, the carrier disappears completely and the power is completely transferred to the sidebands. Increasing the beta increases the number of significant sidebands and spreads the power across the frequencies, and the location of the peaks and troughs shift to the right, meaning the first peak occurs at a higher beta. The small beta gives the narrowband frequency modulation with strong carrier and few sidebands, and the large beta gives the wideband frequency modulation with many sidebands and weak or zero carrier. This graph helps to visualize how the modulation index beta affects the spectral power distribution. Now let us understand the behavior of this nth order Bessel function j and beta. As the value of n increases, j and beta becomes smaller and approaches to 0 for a fixed beta, especially when n is very greater than beta. An infinite series expansion for j and beta is given by j and beta is equal to summation from k is equal to 0 to k is equal to infinity minus 1 to the power k beta by 2 to the power n plus 2k divided by k factorial into n plus k factorial. However, for small values of beta, this j and beta may be approximated by j and beta is equal to b by 2 to the power n divided by n factorial. This approximation simplifies the analysis when beta is very less than 1. There are some special values for this nth order Bessel function. Normally, j not beta is equal to 1 and j and beta is equal to 0 if n is a non-zero integer. Bessel function exhibits key properties that help in frequency modulation analysis. For even and odd value of n, j and beta is equal to j n minus beta if n is even, and j and beta is equal to minus j n minus beta if n is odd. So negative order relationship is the j n minus beta is equal to minus 1 to the power n j and beta. So j and beta is equal to j n minus beta if n is even, and j and beta is equal to minus j minus n beta if n is odd. For large n, j and beta is equal to 0 if n is very greater than beta. Again, the frequency modulated signal can be written as st is equal to AC integration from minus infinity to infinity j and beta cos 2 pi fc plus n fm into t. The discrete spectrum of the angle modulated signal is obtained by taking the Fourier transform on both sides. The general notation of the time frequency duality is shown as st is transformed to the frequency domain as s of f. Here, st is the signal in the time domain, s of f is the corresponding spectrum in the frequency domain, and this is the standard representation when transitioning between the domains. A cosine wave in the time domain corresponds to 2 delta function in the frequency domain located at plus minus fi, or cos 2 fit can be written as half delta f minus fi plus half plus delta f plus fi. Delta function normally gives impulse at a specific frequency. If a component of the signal S1t contains a sinusoidal term at a frequency fi, then its spectrum is S1t less than or equal to s of f into del f minus fi plus del f plus fi. Each component of the signal st, namely the term j and beta cos 2 pi fc plus nfm into t, corresponds to a sinusoidal component in the frequency f equal to fc plus nfm, and spectrum is given as Fourier transform of cos 2 pi fc plus nfm t will be half delta f minus fc minus nfm plus delta f plus fc plus nfm, and the Fourier transform of the entire signal st will be s of f equal to ac by 2 integration from minus infinity to infinity j and beta delta of f minus fc minus nfm delta plus delta of f plus fc plus nfm. So this is the spectral representation of the frequency modulated signal for singleton modulation. Let's look at the amplitude spectrum of the frequency modulated signal. This graph shows the amplitude spectra for the modulation indices beta is equal to 0.5, 1 and 2. As the value of beta increases, more sidebands appear and the bandwidth increases. Sidebands are spaced at the frequency fc plus n into fm for all the values of beta. Amplitude of the sidebands follows the Bessel function j and beta. In this figure, fm is decreased to increase the beta while keeping the del f constant. Absolutely, for plot 1, when beta is equal to 0.5, few spectral components, only the carrier and the first order sidebands fc plus fm are significant. It resembles the amplitude modulation spectrum with two main sidebands. Narrow bandwidth or bandwidth is equal to 2 fm is suitable for voice communication. Most of the power is concentrated in the carrier and the nearest sidebands. Narrowband frequency modulation occurs when beta is less than 1. In this case, it is equal to 0.5. For beta is equal to 1, this is the transition zone, and more sidebands appear at Fc plus Fm, Fc plus 2 Fm are visible, and carrier amplitude starts decreasing due to the power spreading. Bandwidth starts expanding beyond the narrowband approximation. This shows the transition point from narrowband to wideband behavior, and this modulation has moderate fidelity with slightly better noise emanation than beta is equal to 0.5. For beta is equal to 2, we will have the wideband frequency modulation. This shows the significant energy in sidebands up to plus minus 5 FM from Fc. It also shows much wider bandwidth up to 6 FM following the Carson's rule. And the carrier amplitude is even lower due to the more power in the sidebands, and the sidebands are symmetric and numerous in the form of Fc plus minus n into Fm, where n is from 1 to 5. This wideband has high fidelity, better noise reluctance, typical for music and broadcast FM. This unique behavior, where the carrier amplitude varies with the modulation index beta, is a key distinction between the amplitude modulation and frequency modulation. It plays a crucial role in determining how the transmitted power is distributed across the frequency spectrum in the frequency modulation systems. The amplitude spectrum of a frequency modulated signal is highly dependent on the value of beta. Based on this, FM signals can be broadly classified into two types: narrowband frequency modulated signal and the wideband frequency modulated signal. In the narrowband frequency modulation, the spectrum contains a stronger carrier components at Fc along with the two dominant sidebands at Fc plus minus Fm. This form of frequency modulation is bandwidth efficient but offers limited noise immunity and approximating the bandwidth of 2 Fm. This spectrum is consists of significant sidebands spaced at the intervals of Fm. As the value of beta increases, the number of these sidebands grows, leading to a much wider bandwidth. The bandwidth is estimated using Carson's rule, and the bandwidth is equal to 2 into beta plus 1 into Fm. Wide bandwidth frequency modulation provides better noise resistance and high signal fidelity, making it ideal for high quality applications like frequency modulation radio broadcasting. In summary, the spectral characteristics of the frequency modulated signal are directly influenced by the modulation index beta. For the small value of this modulation index beta, the frequency modulation closely resembles amplitude modulation with a limited number of sidebands, and for large value of beta, the power is spread across the many sidebands, resulting in a broad, rich spectrum. This concludes our discussion for this lecture. In the event that you have any question regarding this presentation, feel free to post them in the comment section, and don't forget to hit the subscribe button. See you in the next one.